Astronomers around the world have reached a remarkable milestone with the sharpest image ever captured of the interstellar comet known as 3I/Atlas, using the extraordinary resolving power of the NASA/ESA Hubble Space Telescope. This unprecedented observation marks a significant step forward in humanity's ability to study objects that originate far beyond our own solar system. Interstellar comets are exceedingly rare visitors, and each one offers a fleeting but invaluable opportunity to examine material formed around distant stars. The clarity of Hubble's images has allowed scientists to push beyond earlier ground-based observations, refining estimates of the comet's physical properties and behavior as it races through our cosmic neighborhood. One of the most important outcomes of Hubble's observations is a more accurate estimate of the size of the comet's solid nucleus, the icy core from which gas and dust are released as it warms. Researchers report that the upper limit of the nucleus diameter is about 5.6 kilometers, although it could be dramatically smaller, perhaps only around 320 meters across. This wide range reflects the inherent difficulty in directly observing the nucleus itself. Even with Hubble's exceptional vision, the nucleus remains hidden within a surrounding cloud of dust and gas known as the coma. As sunlight heats the comet, volatile ices sublimate and carry dust away from the surface, creating a bright veil that obscures the solid heart within. Despite this limitation, the tighter constraints achieved by Hubble represent a major improvement over previous estimates and help scientists narrow down realistic models of the comet's structure. The challenge of directly observing the nucleus highlights why collaboration between multiple observatories is so crucial. Data from other powerful instruments, particularly the NASA/ESA/CSA James Webb Space Telescope, are expected to play a vital role in refining our understanding of 3I/Atlas. While Hubble excels at capturing fine details in visible and ultraviolet light, Webb's sensitivity to infrared wavelengths allows it to probe the chemical composition of the gases and dust surrounding the comet. By combining these observations, astronomers hope to determine what kinds of ices are present, such as water, carbon dioxide, or more exotic compounds. This chemical fingerprint can reveal clues about the environment in which the comet originally formed, offering a rare glimpse into the building blocks of a distant planetary system. In addition to constraining the nucleus size, Hubble's images reveal striking details of the comet's activity. The telescope captured a plume of dust erupting from the side of the comet facing the sun, along with the faint suggestion of a dust tail streaming away into space. This activity occurs as solar radiation heats the comet's surface, causing frozen gases to vaporize and eject dust particles outward. By analyzing the brightness and structure of this dust, scientists can estimate how quickly material is being lost from the comet. The results indicate a dust loss rate consistent with comets that are first detected at distances of around 480 million kilometers from the Sun. In this respect, 3I/Atlas behaves much like comets that originate within our own solar system, suggesting that some fundamental physical processes are universal, regardless of where a comet was born. Despite these similarities, the most profound distinction between 3I/Atlas and typical comets lies in its origin. This object did not form in the cold outskirts of our solar system, but instead emerged from another planetary system somewhere else in the Milky Way galaxy. Its presence here is a reminder that stars and their accompanying debris are not isolated islands, but part of a vast, dynamic galactic ecosystem. Over billions of years, gravitational interactions within its home system likely flung the comet into interstellar space, setting it on a lonely journey through the galaxy. Only by chance did its path eventually intersect with our solar system, allowing astronomers to briefly study this ancient traveler. One of the most astonishing properties of 3I/Atlas is its incredible speed. The comet is tearing through the solar system at roughly 210,000 kilometers per hour, making it the fastest visitor ever recorded passing through our planetary neighborhood. Such an extreme velocity provides compelling evidence that the comet has spent an immense amount of time drifting through interstellar space. Over billions of years, it would have experienced countless gravitational encounters with stars, star clusters, and nebulae. Each close pass acts like a cosmic slingshot, subtly altering the comet's trajectory and gradually increasing its speed. The longer an object wanders the galaxy, the more opportunities it has to gain momentum, and 3I/Atlas appears to be a prime example of this process. This extraordinary speed has important implications for how scientists interpret the comet's past. A high velocity suggests not only a long interstellar journey, but also that the comet has survived extreme conditions for an immense span of time. In the depths of interstellar space, far from the warmth of any star, temperatures can plunge to just a few degrees above absolute zero. At the same time, the comet would have been exposed to cosmic rays and other forms of high-energy radiation capable of altering its surface chemistry. Studying how 3I/Atlas responds as it warms near the Sun may help scientists understand how such prolonged exposure affects icy bodies, and whether interstellar comets preserve pristine material from their birth environments or evolve significantly over time. The discovery of 3I/Atlas itself is a testament to the growing sophistication of modern astronomical surveys. The comet was first detected by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, on July 1, 2025, when it was about 675 million kilometers from the Sun. ATLAS is designed to scan the sky repeatedly, searching for moving objects that could pose a threat to Earth, but it also plays a crucial role in identifying rare and unusual visitors like interstellar comets. Once detected, the comet quickly became the focus of intense follow-up observations from observatories around the world and in space, as astronomers raced to gather as much data as possible during its brief visit. Timing is critical when studying such objects, as their visibility is often limited. 3I/Atlas is expected to remain observable by ground-based telescopes through September, giving astronomers only a narrow window to collect data before it passes too close to the Sun to be safely observed. During this phase, the glare of sunlight will overwhelm most instruments, effectively hiding the comet from view. If predictions hold, it should reappear on the other side of the Sun by early December, offering another chance for observation as it continues its journey out of the solar system. Each observing opportunity is precious, as once the comet departs, it is unlikely to ever return. Beyond the immediate scientific findings, the study of 3I/Atlas carries deeper implications for our understanding of planetary systems throughout the galaxy. Interstellar comets are natural samples of material formed around other stars, delivered directly to our cosmic doorstep. Unlike distant exoplanets, which can only be studied indirectly, these objects allow astronomers to analyze real matter from beyond our solar system. By comparing the composition and behavior of interstellar comets with those formed locally, scientists can test theories about how common certain materials and processes are across the galaxy. Each discovery helps answer fundamental questions about whether planetary systems, like ours, are typical or unusual. The observations of 3I/Atlas also highlight the complementary roles of different space telescopes. Hubble's sharp imaging provides precise measurements of structure and activity, while the James Webb Space Telescope offers unparalleled insight into chemical composition. Together with ground-based observatories, these instruments form a powerful network capable of responding quickly to rare events. As technology continues to improve and survey systems become more sensitive, astronomers expect to discover more interstellar visitors in the coming years. Each new object will add another piece to the puzzle of how planetary systems form, evolve, and interact within the Milky Way. Ultimately, 3I/Atlas serves as a powerful reminder of the vast scales of time and space that shape our universe. This small, icy body has likely been traveling for billions of years, long before Earth formed, carrying within it a record of conditions around a distant, unknown star. Its brief passage through our solar system is a momentary crossing of cosmic paths, yet it offers insights that reach far beyond its fleeting appearance. By studying this comet in detail, astronomers are not only learning about a single object, but also expanding our understanding of the dynamic, interconnected galaxy we inhabit.